Hello, my name is Sean Seyrev. I'm a master's student in Ben-Gurion University. This research is called Solving the Watchman route problem optimally on a grid with heuristic search. This is a joint work with Tamir Jaffe, Margarita Lopatin, and Ariel Fellner. In our problem, the goal is to find the shortest path inside the grid in such a way that we can see all the free cells of that grid. The input of this problem is a grid map and an agent starting location. The output of the problem is a minimal cost valid path. A valid path is a path that after traveling it, the agent has seen the whole map. You can see at the left picture that the agent is starting at the left bottom cell, and the solution is presented as red arrows. The movement of this agent is up, down, left or right, meaning four-way movement. Line of sight, Bressenham loss, or Bress loss, a function commonly used in computer graphics. You can see at the right picture the agent marked as green, and the gray cells are the cells that he can see from that location. To solve this problem, we use heuristic search. So now we'll define the problem as a search problem. A node is defined by the current agent's location and the list of all the cells that has been seen by the agent until now. We call it SeenList. The operator is moving the agent to a neighbor location and adding to the scene list all the cells that can be seen from the new agent's location. The start node contains the agent's starting position, and the scene list contains only the cells that has the line of sight to that location. A goal node has a scene list that contains all the free cells of a grid map. Notice that the agent's location can be anywhere on that grid map. To solve this problem, we use A*, a best first search algorithm, and we developed three heuristics. Our heuristics are based on a graph constructed from the grid map. Our graph contains three types of vertices that represent cells from the grid map: pivots, watchers, and the agent. The pivots, colored red, are a set of cells which are not in the scene list. The watchers, colored yellow, are the cells that have line of sight to any of the pivots. And finally, we add the agent vertex, colored green, to the graph. The graph contains edges of two types. The first type are the edges between a pivot and its watchers. Their weights are zeros. For the second type of edges, we connect any pair of vertices which are not pivots, with the weight of their true distance in the grid. For the pivot set, we choose cells which don't have any shared watcher. To simplify the graph, we keep only the frontier watchers. Those are watchers that the path from the agent to them doesn't pass through another watcher of the same pivot. As can be seen in the example, C and F are pivots, A, I, and E are watchers, and B and H are left out because they are not frontiers. A path on this graph that contains all the pivots is a lower bound to our problem. So in order to compute our heuristics, we use the MST, minimal spanning tree, and the variant of the traveling salesman problem, TSP, which has a known starting location, and the path isn't a cycle. Using four-way movement and these heuristics is our first method, which is called basic expansion. We developed a second method, which changes the operators. Instead of using four-way movement, we say that the agent can move only to the frontiers which are connected to it at the graph. For example, I, E, and A. When generating a new node with this operator, the agent's location is updated to be the watcher's location, and we add to the scene list all the cells that can be seen when traveling that path. We call this Jump to Frontiers, or JF. The bottom picture and the table next to it show our experiments on a grid map with a size of 11 on 11. For this experiment, we used four algorithms. The first is BFS, a blind search, and the others are based on A*. Singleton is a basic heuristic that we used, and the two graph heuristics mentioned before. The left column shows the basic expansion, and the right one shows the jump to frontiers. As can be seen, the TSP heuristic performed best. Also, jumping to frontiers significantly improved the results. Overall, when using TSP and jumping to frontiers, we can improve the results by 3 orders of magnitude. The full paper for this research was accepted in ICAPS 2020. Thank you for listening.